Good evening, everyone. This is Carl Tammer representing the Iowa-Illinois section of the IEEE. I'd like to welcome everyone to tonight's meeting and thank you all for your participation. Tonight's talk is of particular interest to power engineers. I'm one of them. I will say that as long as I've been in the power industry, the one constant has been the change in the industry. And as we'll hear tonight from our esteemed speakers, talking, we'll be discussing fault currents as our electric system is changing. There's more distributed resources injecting short circuit currents, into the system when there are faults, and arc flash mitigation, is certainly an historically big issue and important issue for safety of our electrical workers. And Jimmy and Andrew will be introducing an innovative product that will help mitigate these faults. So, first up will be Jimmy Bowe with G&W Electric, and joining him will be Andrew Garcia, application engineer with G&W. So, gentlemen, please take it away.
Thank you. Thank you for the intro, Carl. I'll be kicking it off. And the topic today is mitigating incremental short circuit fault levels in incremental system. Once again, my name is Jimmy Bowe, and I am the Global Product Manager for CLIP. That stands for Current Limiting Protector. And like Carl mentioned, I will be explaining the features and value proposition of the CLIP, but I will only be talking about that. We'll be presenting about the problem, which is these short circuit levels that keep increasing worldwide in the power grid, and both traditional and new solutions to address such problems on the grid. A little bit about my employer. So G&W Electric provides electrical solutions to strengthen the grid, right? We are a global manufacturer of commercial electrical equipment that makes the power grid more resilient and reliable. Again, today we're going to talk about some of these equipment in the portfolio. So first, I want you guys to focus on the picture to the right, which is one of such cases, right? This is a catastrophic event in a manufacturing facility due to short circuit fault. And what are those faults? They are insulation breakdowns due to a variety of reasons, and that is faulty equipment, human error, pollution, or electricity overload. So looking at this picture, we pose you three questions. Are you prepared for such events? Is your system rated to prevent these events? And how can I prevent this from happening? And we hope that at the end of this chat, you will be able to favorably answer all three questions. So yeah, like Carl said, the one constant is that the grid is always changing. We are really experiencing a power revolution. That's due to the technology advancements that the grid is going through. Ever increasing demand for reliable energy. Electrical systems have been forced to grow and accommodate such an increase, and then proportionally, so the faults keep increasing. And what does that do? It leads to problems like increased cost due to repairs, project delays, the amount of time it takes to repair this equipment, and safety issues, right? Down to when there's catastrophic events, it could be as bad as the loss of life. Well, how do we prevent such events? Well, we have the traditional protection, which sometimes is not sufficient, and we have the new current limiting devices, among others, that can be considered, and we're going to discuss today. To drive the point home, Why are fault levels increasing? Well, because the increased energy demand that is driven by the power grid revolution, like I said. And what's driving that? Well, we know all of them, but primarily data centers. Um, they're leading the way in markets as cloud computing, data mining, analytics, and above all, AI. Right? We hear AI everywhere. It's in our businesses. It's everywhere we go. It's in our phones. It's in our alarm clocks. AI is everywhere. Right? We're talking to Siri every day, and those that the AI in particular has a power demand hockey stick, right? Like it's just a energy guzzler. Besides that, we also see electric vehicles, two-way flow of power, uh, of power due to renewables, wind, solar, and battery energy storage. The grid, the aging grid wasn't designed for these additions to the grid, right? DER is another one. So again, think about the power distribution changes and how it's growing. So the now I'll start talking about the traditional protection, and then Andrew will go into the new, the more current protection schemes. So some of the traditional ones are fuses, which I'll give you some pros and cons. It quickly interrupts and limits the flow of current, right? We all know them. They limit both magnitude and the duration of the fault. Some of them are the backup fuses and current limiting fuses. Pros, widely available, inexpensive, and low maintenance. The cons is that they lack flexibility. One, they need to be replaced, right? When they blow, you got to get a new one. The limited availability at higher current ratings in particular, most of them do not live in the thousands of amps of continuous current. And at the end of the day, it might not be enough. When I say lack of flexibility, I mean that a lot of them conform to the traditional TCC curves of fuses. The other ones that we run into all the time, and all of us should be familiar with, are reactors. They're passive components, and you're basically adding impedance into your system. They limit magnitude of the fault, and this is a key factor, that you limit the magnitude, not the duration. Some of them are current limiting reactors that reduce the fault on in a three-phase system. It'll reduce the fault of a three-phase system. And the other one is a neutral ground reactor that reduces the fault at ground faults. Pros, they're again widely available. They have higher ratings. You can design for high current levels, and they are low maintenance. But the cons, it's a large footprint, poor power quality due to the losses in the system. Poor power quality due to the voltage sags in the system. When you introduce a reactor, you can introduce voltage drops into your system. And low power efficiency is that impedance that you're introducing there generates losses, which could be lower energy that then translate to loss of revenue. And then just to drive the point home, then to the difference in size, you can see some of these CLRs could be 3 stories high, and but in contrast, your current limiting fuse alternative could be 5 feet by 2 feet, and much more compact. Now, Andrew Garcia will take over, and we'll talk about the more modern current limiting devices.
Thank you, Jimmy. If any of you have any questions at any time, just feel free to ask. In any case, I'm going to go over some of the innovative features of the new style of modern current limiting devices. So there's a lot of new developments in these current limiting devices. These increasing levels of fault current in the grid are causing a lot of change, and those are requiring new advancements in technology. We need to have devices that detect faults faster. We need to have devices that reduce the duration that a fault goes on, and we need to have devices that reduce the overall look-through energy. Anything that can reduce the severity of a fault is going to be a good change. We're going to go over some specific devices of these new style of technologies that are going to be increasingly common over time. So solid state breakers, superconductors, and current limiting protectors or clips. So let's go over, let's start with the solid state breaker. This is a new modern device. This is a type of circuit breaker that uses semiconductors instead of mechanical components to function and interrupt faults. The big advantage of this is that this ultimately clears faults in microseconds and not milliseconds. So not only is it current limiting, it's basically interrupting that fault waveform instantaneously and almost completely eliminate that arc flash and fault current. It's going to limit the magnitude and duration of the fault, far less than half a cycle, therefore considered a very current limiting device. So obviously the pros are pretty apparent. They're fast operating devices. They have a long lifespan because they don't rely on mechanical parts, especially in areas where you need to continuously use some kind of device to interrupt faults. Because of the electronic nature of the solid state breaker, you have vastly enhanced ability to control when this device trips. And ultimately, you have a device that completely eliminates or significantly reduces arc flash in your system. Of course, there are some significant drawbacks as well. Things sound good, too good to be true. They usually are. They are very expensive. There are limited ratings, so very common more in the low voltage spectrum of things. The higher you go in terms of voltage class, continuous current rating, and short circuit current rating, the bigger and more expensive they become and may not even be available. There's also a limited amount of maintenance you can actually perform on these devices if they're not functioning properly. It's not like a mechanical device that you can just go in and tune up. You're probably going to have to either replace a large chunk or the entire device entirely and replace it, which can get also expensive. Another very up and coming technology that we're starting to see a lot of are superconductors. These are electrical wires made of superconductive material. When cooled to a low temperature, they have close to zero electrical resistance. Now you can use this property, if you think about it, if you can rapidly increase that resistance, which shouldn't be too hard when they're cooled to very below zero, by increasing that temperature, therefore lowering that fault current by adding resistance or impedance to the system. One drawback of this method of current limiting, though, is it requires long lengths of cable to have this current limiting effect. So this is very much limited at this point to large industrial facilities and utilities. So the pros are pretty self-evident. There's zero resistance, meaning that you're not going to suffer any voltage sags or any power efficiency losses from using this. There's a very high current density. You only need, the size of these conductors are going to be much smaller than ones that would have an equivalent rating. Overall, they're just highly efficient at what they're doing in terms of just transporting electricity. Once again, there are cons. At this point, they're expensive. Superconductive material is not cheap. They introduce cryogenic hazards to your system that your workers will have to be trained on, or technicians will have to be trained on. And once again, this requires significant cable length in kilometers or miles in order to achieve a current limiting effect. If it's smaller than that can achieve a current limiting effect, then what you're going to do is you're going to have a lot more available bulk current in your system then that you're going to probably mitigate with some other means that are discussed within this presentation. And there should be, okay, well, this is a visual demonstration of what all these different devices are. You can see on the left an example of a solid state breaker made by ABB. You can see very much that there's no visible mechanical parts, and there's literally just a black monolith with the word open on it in front. That gives you indication of whether or not it's open or closed. You have an example of a superconductive wire or conductor over to the top right. Just gonna basically what happens is that liquid nitrogen gets pumped through there to cool that device down to below zero to a temperature where superconductivity is possible. In the bottom right, you have the current limiting protector, which is a definitely very cool device. Hopefully I'll have a slide to talk about it, but it has a bus bar that goes straight through. You can see in line, like inside the clip of the blue cylinder, where there would be pyrotechnic charges lined in order to blow apart that bus bar, making that path highly resistive and then sending that current through the current limiting fuses in parallel. How do these devices compare? In terms of cost, current limiting protectors would definitely be the best of the three. They definitely cost less at this point relative to solid state breakers and superconductors. Superconductors, due to their long lengths needed and the special materials required, they definitely do cost a significant chunk of money if you do need them at some point, with solid state breakers coming in between the two. I do anticipate, though, both superconductors and solid state breakers going down probably pretty significantly in price in the long run, though, as the years go on. Once again, in terms of complexity adding to your system, current limiting protectors are once again going to win in that scenario. That's because of the superconductors adding a lot of different technical aspects to your system, such as cryogenics and any kind of electrical controls that would be needed to control that. And solid state breakers would also require some additional programming as well. Current limiting protectors just need to change a single trigger level in regards to that. So current limiting and arc flash both can be kind of combined into one, and solid state breakers are going to take the cake on that. Once again, that's clearing the total fault in microseconds and not milliseconds. Clearing our level of arc flash or incident energy is going to be directly related to the clearing time of a fault, along with the available vaulted fault, and a current limiting device is going to limit that available fault current. So therefore, a device that can do that trip in microseconds is just going to be almost unbeatable in terms of both current limiting and arc flash. That being said, current limiting protectors do come in second. They do clear that fault extremely quickly, 1/4 to 1/2 of a cycle, depending on the type of fault. And as a result, they do have a significant limiting effect in regards to arc flash as well. Superconductors come in last, not because they don't have potential in terms of fast current limiting and arc flash, but because of the more complex setup and the fact that long lengths of cable at this point are required to achieve that current limiting effect. In terms of available ratings, I would say superconductors take the cake. They're just wires. They can be hooked up for a lot of different scenarios. Current limiting protectors then have the second most flexibility, going up to 38 kV voltage class, up to 4,000 or 5,000 amps continuous, depending on the continuous current rating, and then up to 120 kA or 60 kA short circuit rating, depending on the voltage class and whatever current you have available, which is pretty significant when you compare that to alternatives like current limiting fuses. Unfortunately, at this point, solid state breakers definitely take the last, as higher rated solid state breakers require a very large application at this point, which can get very expensive. It may just price itself out of the market if they had it available. In terms of low-level protection, though, current limiting protectors definitely come in last. Current limiting protectors are designed to be a backup device for your worst-case fault scenario. What that means is that it is not going to trigger for low-level fault scenarios. It's only going to activate and reduce fault current in terms of your worst-case scenario. Meanwhile, solid-state breakers can virtually eliminate any fault within microseconds, provided that you're willing to open your circuit. And superconductors would also be able to respond, given that you have enough length as well in a very short period of time. Regards to power efficiency, superconductors obviously come in first. Near zero resistance is almost unbeatable. Current limiting protectors come in second, as it's just a bus bar, copper bus bar in a normal operation. Meanwhile, solid state breakers do require a lot of energy passing through those semiconductors, meaning that there is a very small power loss that is incurred when using a solid state breaker device. It's usually not very significant, but it is there and definitely something to keep in mind.
Okay, Andrew, Is this the slide that you were looking for? Or
there's a pros and cons one too, but yeah. In any case, here's the more information on the current limiting protector. It's called or clip, as we call it for short. It's an electronically sensed and triggered device. It's very fast acting. It clears a fault in 1/4 to 1/2 of an electrical cycle. And that says consistently. It doesn't depend on any kind of TCC curve or let through curve like a normal current limiting fuse would. It's going to consistently hit that trigger level. Once it hits that trigger level, limit fault current to approximately the same amount. It is a single shot device, meaning that you are going to have to go and replace the blue cylinders you see off to the right when the clip does activate and trigger and respond to a fault, as that bus bar inside the bottom blue cylinder is going to be blown apart, and the current limiting fuse up top is going to be melted and opened as well. We do offer high continuous current ratings. That's something we like to emphasize because that's definitely the big differentiator between us and alternatives like breakers and fuses. Up to 4,000 amps continuous, up to 38 kV, and then up to 5,000 amps continuous, up to 15.5 kV. We can achieve this because there is a copper bus bar that's, under normal operation, this is just a copper bus bar. And when it does trigger with a current limiting fuse in parallel, of course, the bus bar is going to be the less resistive path relative to the current limiting fuse. So under normal operation, all current is going to go through that copper bus bar. Once the fault occurs, though, that pyrotechnic charge is going to activate extremely quickly and blow apart that bus bar and commutate all that fault current into the parallel current limiting fuses, melting and clearing that bulb extremely quickly. Once again, between 1/4 and 1/2 cycle total for clearing time. Outdoor and indoor use by default, meaning that these can be installed outdoors, behind a fence or pole top without any issues, but outside of an enclosure. But they also can just be installed indoors inside an enclosure if you would like that as well. Mm-hmm. Medium voltage and low voltage options are available up to 38 kV, and ultimately something that emphasizes that when a clip device does trigger, all that fault energy does get contained completely safely inside those blue cylinders that you can see off to the right. There is no additional hazard from the pyrotechnic charges. That is something that a lot of people ask and have concerns about because that's not something that you normally see in an electrical system. But we've never, all of that excess energy, all that blast energy, shrapnel gets completely contained within that blue cylinder. And the only additional hazard that you would be experiencing is a loud noise being generated, similar to that of a small caliber rifle. But I don't think anybody here is they're in environments where you experience a lot of loud noises. So that should be something that all of you guys are already experienced and mitigating with and dealing with.
Any questions to this point? We're gonna get to practical applications.
Yeah, sure. So what do you look like when you talk about practical applications of current limiting devices? Hopefully I'll give you guys some few pointers on how to actually implement a lot of these devices into your systems. So what are the overall benefits? Why should I use a current limiting device? Well, it gives a myriad number of benefits. It lets you use lower rated equipment, save some money, potentially save some lead time if you can get that equipment sooner. You can safely operate over-duty equipment longer. If you guys upgrade the amount of capacity in your system, your equipment gets over-duty as a result. You can use a clip or other current limiting device to lower that available fault current so you can safely operate that equipment. You can upgrade the reliability of your system or increase its capacity by paralleling sources in the system, but also mitigate the need for needing a system upgrade by using a current limiting device by having both those sources connected and increasing the amount of available fault current in the system. Ultimately, they also reduce arc flash risks by reducing both the magnitude and duration of a fault. You have the potential from eliminating power quality and power efficiency issues from using current limiting reactors or high impedance transformers or other similar devices. And then ultimately, you can also retrofit existing systems without needing to upgrade infrastructure by making sure that whatever equipment you're installing matches the same ratings. So what are some best practices for using and specifying these current limiting devices? Well, my recommendation would be to have them specified at the beginning of the project. Worst case, you don't need them and you end up saving money. Best case, you just kept the project on time and you already anticipated a problem that a customer might have. You want to pay very close attention to downstream inrush current. It's important because inrush current of large electrical devices such as transformers, capacitor banks, motors, etc., can be large enough to trigger a current limiting device. This is less of a concern on the low voltage side and more of a medium voltage issue, but still something to look out for. With any current limiting device, that would really be an issue. Save something that operates passively, like the current limiting reactor. So there are workarounds for this, especially with the electronically activated versions, but you might have to just get used to having some nuisance strip risks if you're using fuses and have some inrush sources downstream. So first off, you want to make sure you understand what the user actually wants. And by that, I mean some of the following examples. So they want something similar to a current limiting fuse, but want to avoid downtime. Recommendation then, use a reactor or a current limiting protector instead. A reactor is just going to operate continuously. There's always going to be limiting current. Therefore, if a fault does happen, it's just going to be isolated to wherever the fault is. Furthermore, a current limiting protector is only going to be used as a backup device only in your worst case scenarios. So it's really only going to cause downtime in your system if a really bad fault happens, which you probably would like anyways. Other scenarios, you want to use a reactor, say a current limiting device, but want to avoid power quality issues. My recommendation then would be to use a solid state breaker, current limiting fuse, or a current limiting protector. Any device that would have a very low impedance in there will end up causing have a low impedance and therefore have very limited power quality, causing issues as a result. Some people have limited space. Therefore, you want to use a small device like a current limiting protector or current limiting fuse. And for scenarios where they can't have any downtime at all, your only option is really to use a current limiting reactor. So how do you coordinate these current limiting devices with other protective devices in your system? Well, you're going to ensure that your current limiting device only activates or trips when necessary. You ultimately want to minimize what the probability that the current limiting device is going to trip when the regular protective device is going to handle the fault. So you want to make sure that whatever current limiting device you're using should have the most TDC curve available, either through selecting the best device or setting the device to the best possible settings. That can be done by using either software or manufacturer recommendations. If you use a device that operates passively like a reactor, probably already just need to make sure you're following local regulations and you've accounted for any power quality issues that that accounts for, and making sure that's properly protected at both ends of the device. And ultimately, once again, make sure to account for inrush current when you're going through this. So here's one example with a nuclear power plant. Here, a reactor was used to limit fault current to prevent starting of large pump motors. However, this ended up causing a lot of power quality issues at the site due to voltage drops. They did not like that at all. It was causing a lot of issues. They then were able to use clips, current limiting protectors, to bypass those reactors to avoid any kind of voltage drop from that reactor impedance. Therefore, they were able to get those pumps started, pump motors started, and they were able to operate their site as normal. They also ultimately saved a significant sum of money by mitigating any power loss that would have occurred from using those high impedance reactors.
Right? Yeah.
All right, we do have a question. Can modern protection devices replace traditional protection devices one for one? There are situations where that is possible. For example, a clip could replace a reactor in a lot of situations. In other situations, no. I mean, superconductors are kind of their new thing. They might be able to replace the need for a current limiting device that would otherwise be needed, but there's no real one-to-one comparison between a superconducting cable and anything else that's available. Solid state breakers can definitely be seen as a replacement for a lot of different devices like fuses and reactors as well. So here's an example for that nuclear scenario, what that bypass scenario looked like in their one line. So they had their reactor, they just simply put their clip in parallel with that reactor. Since under normal operation, the clip is a very low impedance device, it's such a copper bus bar. Well, a current limiting reactor is a very high impedance device. All that current then chooses to go through the clip path instead of through the reactor. Therefore, bypassing that reactor and ensuring that there's no voltage sag issues within their system. Here's another scenario where clip current limiting protectors protect 121 wind turbines from the grid. They were very underrated. This customer actually definitely got some issues with their utility. They got told most of the way through their project that their fault current levels were going to increase. And they found out that a lot of the equipment inside their wind turbines were now underrated when dealing with fault current from the grid. That's important because inside a lot of this equipment for the turbines and around it is very limited in space. There's only so much space you can work with. So if you do not, if there is no replacement for that, then you are kind of in a bad situation. And then you have to find a solution using some kind of current limiting device. By using the clips, they were able to safely energize on time and ultimately kept the project on time and on budget.
We have a case. I'll just add to that one. We have a case study in our website for that one situation. It was an opportunity that actually allowed us to develop a new higher current rating clip. As you can see there in the picture, that's the current limiting protector that's installed there. And I also say that, just like Carl was alluding to, expect the unexpected, right? You will see this very, very often, where these projects take 2 to 3 years to develop. So what the fault levels that were were designed for early in the project are not the same that you see later on. And that's where a current limiting device will come in handy.
An example of kind of how this looked like here on the left, you have the overduty scenario where the turbine equipment feeds and the equipment downstream of that was underrated as a result of the available fault current. The clip was placed in the path of that fault current, therefore being able to reduce that fault current below the requirements, the fault current rate requirements of the system. Therefore, they're normal with the clip in place. That equipment was now safe to use as normal, and they were able to energize on time. So left, you have the overduty scenario. On the right, you have the new not overduty scenario with the clip in place. You can also imagine different scenarios where they use, say, a reactor in that place or even a solid state breaker to be able to limit that fault current below. Here's another application here. When customers use cogeneration, just to explain cogeneration, that's when, say, a industrial facility or a college campus is using a large amount of steam for some kind of industrial process. A lot of these organizations will try to get power from that steam generation as well. And they call that cogeneration. In this situation, that they used clips to isolate the cogen system from the utility during earthquakes, just to reduce the risk. Without the clip, the system would be therefore otherwise be underrated and dangerous during that earthquake scenario. So they're able to use these clips to basically isolate the system and make sure that nothing happens if a very bad natural disaster were to occur. Cogeneration in general can add a lot of fault current to a system. Nowadays, the distributed energy resources being added to people's systems, battery storage units being added to the grid are also causing a lot of fault current to be added to the grid as well. So here you have an example of what the typical cogeneration application looks like. You have 18 kA available fault current from both the right and left transformers, along with 12 kA available fault current from cogen system. That adds up to a total 48 kA fault current, and meanwhile, the downstream equipment is only rated for 40 kA. So how did this solve this issue? Well, they were able to use a clip, as you can see in the next slide. So they installed a clip of that tiebreaker. They were able to therefore limit that available fault current at the faulted location to less than 40 kA and bring that down to a manageable level that the system can handle, and while mitigating the amount of downtime that the system would be down. You can also imagine replacing that clip with other protective devices, fuses, solid state breakers, anything you could really imagine. Reactors. All right, guys, in conclusion, what are some future trends that we'll imagine to see in the long run? Well, current limiting devices are going to continue to evolve. You're going to see these devices be better at limiting the magnitude and time of faults. You're also going to see these devices used more often as the grid evolves in the direction it's heading. As more fault current becomes available, there are going to need to be more solutions to mitigate it, and you'll see these current limiting devices be used more widely in the grid. You're going to see both traditional and modern devices will be used, as there are advantages to using each of the individual devices. So there's not going to be a one catch-all bullet for current limiting needs. It's definitely going to change based on the scenario you're looking at. Overall, I do anticipate that superconductors, solid-state breakers, and current limiting protectors specifically will become more common as time goes on. So here are some key points and takeaways that I'm hoping that you guys will take away from this presentation. One is that the grid is definitely changing. As Jimmy said, it was a power grid revolution. And this revolution is kind of adding a lot of additional capacity to the grid, which is causing fault current to go up. Next step is the importance of current limitation in regards to how to mitigate the additional fault current from this changing grid, and how important that these devices are going to be as time goes on. Hopefully you were able to walk away with what traditional current limiting devices and tools are available, and how many, and some of the modern current limiting devices that are available as well. Hopefully you also got a good idea of how to implement these different devices in a given system, how to interpret what a customer needs, what devices would be good for what specific scenario. And you were able to understand through some real world examples how exactly these get implemented in the real world. All right, now I'm going to open it up. Any questions?
Oh, I'll also add that if you are in the power transmission and distribution world, if whether that is you're an application engineer, spec engineer, product engineer, well, first off, you're in luck because we're in a growing market, and there's a job for all of us out there just because of how the grid is changing, right? And you're gonna have to deal with these issues 100%, right? It's guaranteed. So part of the presentation is to one of my initiatives is to educate these engineers on all these available tools, right? So that when you're looking at a specific project, you know everything that's available out there, including current limiting protectors and devices, and the pros and cons, right? There's an application for all of them, as Andrew pointed out and explained very detailed and eloquently. So hopefully, you came out of it understanding the right application, because there's a right application for each one of these products.
Yeah, looks like we do have a question. Does the NEC speak about modern protection devices? And I would say broadly no. And I think that the NEC in the long run is also going to change as these current limiting devices continue to penetrate into our systems. One thing to consider, of course, is solid state breakers. Once again, they completely clear that fault in microseconds. How is that going to fit in with our current understanding of how series ratings work? via 240.86 of the NEC. These trip extremely quickly. There's no risk of dynamic impedance being added to the system and affecting other parts of the system. So generally, does the solid state breakers that they can prove from the manufacturer via UL certification or something that they can clear in that amount of time, do they really need to also be certified for series rating as well? And as a regards to none of these options at this point are also shown as a arc flash limitation option via the NEC as well, even though these modern protected devices always are all very good devices to limit arc flash. All right. Other than that, I hope that we see the NEC speak more specifically about some of these devices in the future as they become more common.
Well, thanks, guys.
One
Thanks,
reason,
Andrew.
Yep.
Oh, I'm sorry. I didn't mean to interrupt.
Oh yeah, sorry. Just one reason why they might not be as covered by the NEC right now is because typically they're seen at higher voltage levels right now, say medium voltage distribution level, and now they're just getting to the point where they're even being considered for low voltage, like the clip low voltage model. Sorry to interrupt you there, Carl.
Oh, okay. No, thanks. Actually, thanks for that clarification, because I didn't want to put too fine a point on it, but I thought your devices at medium voltage level would be covered by NESC, but what's a letter among friends, right?
True.
I wanted to ask, in terms of implementation, any at the medium voltage level, how would you compare the clip, let's say, to more, to a traditional sectionalizer?
The clip is different from a traditional sectionalizer in its speed. Typically, what differentiates the clip is the ratings it's about to go to. Once again, up to 5,000 amps continuous, 38 kV voltage class, and very high short circuit ratings up to 120 kA. But what really differentiates it from a sectionalizer is its speed. It's going to completely open and clear that circuit within less than half an electrical cycle, which a sectionalizer will typically at least take at least a couple cycles to be able to open and clear that.
Yeah, there's quite a few differences, right? Speed, the ratings, the interrupting rating that it can handle is much higher, and up to 120 kA in certain voltage levels. And I will also say that the trigger level setting, right? So the clip can be set at the factory, and it's the flexibility of setting up that trigger level on where will it trigger for that fault. Actually, they can work in combination. You can use that clip at the line side of a sectionalizer or a switch gear to derate the gear downstream.
Oh, I think by derate he means limit the current downstream.
Yeah. Okay. All right. Yeah. So then you could you could conceivably, or would you? Are there any use cases where you deploy them in coordination with fuses and sectionalizers, so it's kind of like working a classic fuse coordination study? Or
yeah, and once again, these devices are very easy to coordinate. They're used as backup devices. Think of it like a backup fuse if you're familiar with that. They're only going to trigger, they have an electronic setting where they only trigger at very high levels of instantaneous current. So if you can think about it, if you view it on the TCC curve, it's going to be very far over to the right. And if your TCC even shows it half a cycle or less.
Yeah. So, well, like a specific application I'm thinking of is, we might have a situation where there's on a distribution network or a branch, there might be a portion or a section of that has very high incident energy, and you can't, the station breaker just can't clear it fast enough, or the fuse just can't clear it fast enough. Is that like a use case or an application that you might use the clip
Yeah,
for?
that's exactly one of the common applications for a clip, at least. IEEE 1584 shows that clearing time is or arc duration is as that goes up, incident energy is going to increase linearly as well. So by going from like a 5-cycle clearing time with that breaker, say 3 to 5 cycle, go 5 cycle, and with 2 half a cycle with clip, you're already reducing that incident energy by 90% without even considering what the current be limited to as well.
Mm-hmm.
Yeah.
Mm-hmm.
Okay. So, but it does fail catastrophically when it trips. You have to fully replace it.
I wouldn't
Yes.
define that it will only the cat when you say fail catastrophically, it means it operates in a way that it wasn't intended. It fails when it does trigger and blows those pyrotechnic charges. That's a controlled reaction.
Yeah, yeah. So all I was getting at is, I'm sorry, I may have misused the term. Like a fuse, it'll have to be replaced.
Correct.
100%.
It's going to be opened. The fuses in parallel are going to be melted. That bus bar is going to be blown apart by the pyrotechnic charges. So it does need to be replaced.
Yeah. Okay. So after it does operate, would that be a better term?
Yes.
Yeah. Or triggers.
Okay,
Yep.
sorry. So after it operates, I was just looking at the construction of it. Can you easily unbolt it and put a new one on? Is it?
Yeah.
Okay.
There's just some bolts you have to remove on that bus bar and some wires that you have to detach to go to the clip sensing system. Once you do that, you can just take out the loose cylinders, put the new interrupter in, bolt it back in, and reattach the wires, and you're essentially good to go from there.
Yeah. Okay. And then you had some comments earlier that it's safe to be out, like in the general public. It doesn't.
Yeah, it's completely self-contained. There's no additional hazard other than like a loud noise, but if a fall happens, there's going to be a lot of loud noises regardless. So
yeah. So what was I was listening for it and I didn't hear what you said. How loud is it?
like the sound of like a small caliber rifle going off or dropping like a phone book from a really tall table.
Oh yeah. Okay. Well, that's not too horrible. That's not going to wake people up necessarily.
No.
Okay.
Hey, since we're specifically talking about the clip, I wanted to share a video on the operation of the clip. If you don't mind, we have a little time.
Oh, that'd be great. Yeah.
Can you guys see the screen? Can you see the screen?
Yes, I can.
Okay.
Before we do this, we do have a question. Is there
Okay.
indication that the clip operated like a connection to SCADA? The answer would be yes. Every 3-phase clip unit comes with a clip control box. It's hooked up to the clip electronic system, the control system, and inside that control box there's a series of Form C relay contacts that are for triggering indication, and those can be hardwired from there to your SCADA or PLC system, or even directly like an upstream breaker or something, in order to give you indication. There's also going to be visual indication via LEDs inside the control box, along with the physical visual indication on the clip interrupter itself, where a pin juts out of the clip interrupter. All right, Jimmy, and now take it away.
Of G&W Electric.
Can you guys hear it? Can you guys hear the video?
I could hear it.
Hear the sound? Yep. Okay, good.
Current limiting protector, the Clip LV. The Clip LV prevents current from exceeding equipment ratings, avoiding catastrophic failure. It dramatically reduces peak fault currents to minimize damage, protect personnel, and reduce arc flash hazards. The clip is bidirectional. Under normal conditions, the current flows in one direction. The current splits between the interrupter and the parallel current limiting fuse. A copper conductor carries the continuous current through the device from its supply side to its load side. Only a small fraction of the total current flows through the parallel current limiting fuse. The current transformer monitors the level of current passing through the clip. If the current magnitude reaches a predetermined level, The sensing and firing logic system sends a triggering pulse via a twisted wire pair to initiate the fault clearing function. A carefully controlled and fully contained pyrotechnic operation uses a detonating cord to sever the copper conductor and fold it back on itself, opening a gap in the main conduction path. An arc then forms at this gap. The resulting arc voltage across this gap causes the full fault current to transfer to the parallel path through the current limiting fuse. During the time it takes the fuse to melt, the gap recovers dielectrically and the arc ceases to exist. The fuse completes its melt and clears the circuit, just like a conventional current limiting fuse. When the fuse opens, the current flow is quickly reduced to a low level and then fully extinguished at or before the first voltage zero point. This occurs at 1/4 cycle on a purely symmetrical fault, protecting the equipment and minimizing personnel's exposure to hazards. The operation of the clip is fully contained. There are no signs of external physical damages. After operation, the interrupter and parallel current limiting fuse must be replaced before returning to normal operation.
There you got it. So,
what if your smile could go from looking like this?
sorry about that.
Oh, how's your smile, Jimmy?
Hopefully that gave you a high-level explanation of what the clip is about. That the one that you were seeing in the picture is the low voltage, but the medium voltage works in the same operation, right? Same manner.
Yeah, thank you. That was a nice video or animation.
Yeah.
Last question, at least from Carl, on the subject. Can cost price? Can you offer a budgetary estimate?
So I can't for the solid state breakers and the superconductors, but for the clip, Jimmy, would you want to give them like an example of like say a low voltage clip and then like a medium voltage clip?
Yeah. So a low voltage clip ranges around 50, 60K, 60,000 for a 3-phase system, right? We always, for the most part, they go in three-phase applications. And for the medium voltage, it's a wide variety. You can think of it, okay, so we have a version that goes down to 1,200 amps and then go as high as 5,000 amps, right? So and then in interrupting levels, we go up to 120 kA, right? So the amount of fuses and copper that goes, it's a wide variety depending on the model. So they range from
three-phase like a mid-range option, like a 15.5 kV, 2,500 amp, 60 kA kind of thing.
Yeah, that would be like $125,000. $125,000.
Okay, thank you. Appreciate it.
Yeah, I have to wonder, Carl and John, do you guys often see a lot of fault current, like high levels of fault current in your systems? High levels of arc flashes and energy?
Just speaking for myself, we have one or two areas, as I commented earlier, that there's, high incident energy that, it's like a heightened risk for workers, so that we would probably take an outage if we needed, to work in that vicinity. So, an application like this might mitigate, something like that. So, just to allow them to work hot with ordinary PPE.
Yeah, just was wondering how common, like any kind of, if you guys were seeing a lot of construction of data centers or anything in your area or something, might have been adding a lot of fault current.
Oh, yeah. No, this is just as is common variety network.
So some of you are computer society. Okay. John thinks he's cooler than us. He works with computers, huh?
I still love you, John.
I was a physicist, so I do understand how the electrons move.
Oh man, those your physicist buddies must rag on you for becoming an engineer.
Yep. So again, that's it in a nutshell. Just talking about the problem that all these technologies can solve. Obviously, we focus on our product here in GNW, but hopefully, out of this presentation, you got some nuggets on how to solve your problems.
The presentation, make sure to send that out to you guys afterwards if you guys want to review it on your own time. Also, Jimmy has posted both my and his emails in the webinar chat. So if you guys want to reach out for whatever reason, ask more questions, talk about applications, we're more than willing to have that conversation with you.
That's it. Wrap it up and have a good night. I don't know if there's anything at your end, Carl.
Okay, yes, thank you, Jimmy, and thank you, Andrew, for a wonderful presentation. I, for one, learned a lot. It looks like a very fascinating and very useful product. So, if there are no further questions, I just would ask participants if you have any thoughts or suggestions for future topics for meetings. Please please share that with us. And with that, again, thanks everyone for participating, and have a great evening.